All right, hey guys, I hope you're in good health. A few general things before we start class today. As you know, due to the COVID-19 pandemic, all tutorials are now online. That makes this type of tutorial particularly hard to conduct because the main advantage, the whole purpose to running these tutorials is that we can work with each other to solve the problems on a person-to-person basis. But that's really difficult to do in an online format. So the tutorial has been restructured into being a more general lecture format and code along. Also, I am going to warn you guys right now that my Wi-Fi and my computer too is really spotty. So if the feed randomly stops, I apologize and I'll try to fix the problem as quickly as I can. Also, midterm 2 marks are on Avenue, so check those out if you haven't already. And before we begin, let me acknowledge the fact that today's content, there are tons of people on YouTube who have made way better videos about this topic than I could ever hope to. In fact, I'll list some of those videos in the description to help supplement your understanding. One particular person who I want to give a shout out to is Lucid Programming, mainly because I copied a lot of his code for today's examples. So big thank you to Lucid Programming, and subscribe to him if you want to help out a nice, smart dude. Cool. So let me share my screen. Awesome. And I will turn this off. Cool. Awesome. Okay, so today's topic is on the tree data structure. So trees are another common data structure in Python, just like lists or tuples or dictionaries. The special thing about trees is that even though they're just another way to store data, they have a hierarchy. Each node in a tree, a node being just an element, has a special parent-child relationship. In lists or strings, all of the elements are just sequential, one after another. But in a tree, each element or node has a special relationship with all of the other nodes. We can actually take a look in the next slide. So here we have an example of a tree with several elements or nodes. Now, if we take a look at B, for example, we can consider B as something called a parent node. And C, D, and E, we can consider as the children nodes of B. So B is the parent node for C, D, and E, and C, D, and E are all childs of B. This is called the parent-child relationship that exists in trees, the tree data structure. So at the very top of our tree, the top node is known as the root node. So while an individual node can have multiple childs, each node can only have one parent, at least for the scope of this course. So if a node has more than one parent, it is not considered a tree. It does not meet the definition of a tree. Now, trees have a property called depth, and the max depth is just the number of layers in the tree. So what is the max depth of this tree? Can anyone tell? The max depth is 2, exactly. So C, D, and E exist on the second layer. It's at a depth of 2, which is the max depth. B and F are at a depth of 1. Now, a binary tree is a tree where each node can have at most 2 children. So as you see, all of the nodes have at most 2 children. Note they can still have less than 2 children, as in the case of I, which only has 1. And that brings us to the main topic of today, being binary search trees. So a binary search tree is a very useful concept in programming that makes it very easy for us to quickly transverse and search through a large number of nodes. And in today's lesson, we're going to learn how to make this data structure, how to implement it in Python. So there are a few key things we have to keep in mind and understand about binary search trees. One is that all of the nodes are distinct values. That means that no value for a node will repeat itself. As you can see in the example right here, all of the nodes, their values show up just once. Now, there's a specific way that these nodes are connected to each other. If a child node is less than the parent node, it'll be on the left branch of the parent. And vice versa, if the child node is greater than the parent node, it'll be on the right branch. And of course, because the node values are distinct, the child node should not equal the parent node. And we can take a look at this example. So for example, if we consider 8 as being the parent node, it's of course also the root node, but if you consider 8 being the parent node, 3 is less than 8, so it's on the left side. 10 is greater than 8, so it's on the right side. So with that in mind, with those rules in mind, we can actually consider how we would order this sequence of numbers in a binary search tree. So if we consider 8 as being our root node, that'll be on the very top. Take a moment and consider, will the next node be on the left or right of 8? So the next node should be 3. Is 3 going to be on the left or right? Well, 3 is less than 8, so it's on the left. Okay, and for the next one, 10, will 10 be on the left or right of 8? Well, 10 is greater than 8, so it's on the right, exactly. Now for 1, once again, consider where it'll end up. So if we compare 1 to 8, it is less than 8, so it should be on the left side. But this node is already defined, so we have to perform the comparison once again. So 1 is less than 3, so it should be on the left branch. And we can do the same comparison with our last node. So 6 is less than 8, so it should be on the left side. That's defined, so let's do the comparison once again. 6 is greater than 3, so it's on the right side. Perfect. So I imagine from constructing a binary tree, you can understand how it can become very easy to find a specific value in the tree. For example, if we go back to this tree, and I wanted to find the value 6, I wanted to work my way to the value 6. Unlike with the list, for example, there's a very specific way we can get to that value. So if I started at 8, which is right here, and I know I'm looking for 6, well, 6 is less than 8, so it should be on the left side. And once again, I can perform my operation again. I am looking for 6. The value I'm at is 3. Because 6 is greater than 3, it should be on the right side. And using this logic, we can very easily make functions and algorithms in Python to easily search and traverse binary search trees. And that is actually our task today. So our task today is to write a Python program that creates a binary search tree. We're going to have to use object-oriented programming concepts to create this data structure. So that means we'll have to make a class. Now, in addition to that, we're going to make some functions to manipulate our data structure. One of the functions, insert, we're going to use that to correctly add more nodes to our binary search tree. Another one of our functions, search, we're going to use that one to see if we can check to see if a specific node value is inside of our tree. If it is inside of our tree, return true. If it's not, return false. And finally, we'll have a function named depth that returns the max depth of the tree. And we have a test case here for how our tree should look like that we can test with. Awesome. So we can get right into that. But before I start coding, I want to preface by saying that if you look up how to make a binary search tree in Python online, you'll see some examples that are a bit different to what we are coding today. And that is because the best way to implement a binary search tree requires the use of some skills and concepts that we have not learned in class yet. So instead, we'll be implementing it in a bit of a simpler way, but maybe not the most effective way. The goal of today is not to learn those complex concepts, but really just to understand how trees work. So instead, we just want to make sure that our tree, you understand the ins and outs of how trees develop and look like in programming. At the end of the lesson, though, we will go over how we can improve our code, and I'll add some links in the description of how we can make our code better in some proper examples. And you guys can go over those examples and see if you understand the nuances and benefits of the differences. Okay, so let's start coding. So my first step is I'm going to go to Python, and I'm going to make a new program. And I'm going to take a brief pause, just double check that the live stream is still working. So let me check on my phone. Okay, yes, wash your hands, Jeff, awesome. Yes, you can rewatch it later. Sarah, sorry for the late reply. I'm doing fine, Jeff Meat, how are you? Oh, I should probably turn this off. Okay, you guys are very funny. You don't have sound, Yulau? Does anyone else not have sound? I think that might be an issue on your end, Yulau. Okay. All right, so I have made a new program, and I'm going to save it, and I will save it as, let's say, run_5. Okay, so as I said, to make this data structure in Python, we will have to use object-oriented programming. So what I'm going to do is I'm going to make a new class, and I will call this class node. And this class will be for a specific node of the binary tree. And we'll define what properties that individual node of a tree should have. So when I make a class, what is the first method I have to define? What is the first thing I have to make? The init function, of course, the constructor. So I'm going to write def, and what comes next? 2 underscores init, 2 underscores again. And when I make this method, what is the first variable? Self, that's right. And I'm also going to have a second parameter for the init function, that being value, and it'll have a default setting of none. Cool. So my node, each object in my node class will have 3 properties. The first property will be the specific defined value for that node. And I'll call that property self.value. And I'll make it equal to whatever value I pass in, with the default value being none. Now, as I said, in a binary search tree, each node can have 2 children. So I'm going to make 2 potential children too for my node. I'll say self.left_child is equal to none, because it might not have any children to begin with. And likewise, I'll make another variable, self.right_child. And I'll make that equal to none too. Cool. and we'll add another function to this class later on. So if we go back to our challenge, so it said to make a binary search tree using object-oriented programming. Well, we've made a class, and we now have to make these functions to manipulate our data structure, our class, or our instances of the class. So the first function is insert, and the job of insert is to correctly, that's the key thing, correctly connect more nodes to our initial root node. Okay, so I'm going to go back to my program, and I'm going to write def, the function name insert, and this will have two variables. The first variable will be node. It'll be an instance of the node class, and we can consider this as being the root node, the node at the very top of our binary tree. This one right here. I was thinking of naming it root node in the code, but thought that'd make it kind of confusing later on. And the second variable we'll pass in is the value of the new node we're passing in. So this is our existing node, and this is the value for the new node we're passing in. Cool. And now we have to consider, where does this value go in our binary search tree? So let's consider this. If we're passing in a node, and if at the beginning the node has no value, it's the first instance, well, we should just make that equal to whatever value we're passing in then, right? So if we're at the beginning of our binary search tree, if we're at this stage at the very beginning, we should just make the value equal to the first node if there's no other branches. So what I'm going to do is I'm going to see if my initial node is not initialized. And how can I check that? I'll write an if statement, if node dot value. And how do I know if the node dot value is not initialized? I'll set that equal to, I'll set my condition equal to is none. So if it's set to none, that means this value is nothing yet. It does not have a value passed in, and I'm going to make it equal to something right now. So I'm saying if the node is not defined yet, just make it equal to this value. So of course I could do that by just writing node.value is equal to value, but that's not a best practice. Instead, I'm going to go back into my class and I'll write a function def set value. I'll write a set function of which I'll have two variables, self and value once again. And I'll just say that self.value is equal to value. Cool. And I can change this to being node.setValue, and I'll pass in value as we see. Awesome. So if the node value is not set, we're just going to set it into the new value we're passing in. Now, if this node does exist, if it's already defined, what do we have to do next? So if we already have an existing node, how do I add the next value? What do I have to consider? I have to consider if my new value, 3, is greater than or less than the pre-existing value. So let's code that up. Let's put that logic in code. So I'll say else if value is less than node.value. And if it's less than, we're going to go on the left side or right side. The left side. So if it's less than, we'll make the value equal to the left child, but only if the left child is not defined. So I can copy the same logic I have here. I can say if node.left underscore child, if that is equal to none, I will just set the left child equal to this value. Cool. Okay, But what if this value is defined? What happens next? Let's say we're at not this stage of the search tree, but at not of this stage, but this stage. So if we're passing in another value and we're going to go on to the left branch, but that is already defined, what should we do next? How do you perform the same operation down here? Any ideas of how we can perform this function again? Anybody write in the comments what the answer is? Recursion, yeah, that's it. Perfect. Okay, so let's make a recursive function. So I'll say I will then make another comparison saying else. If it is defined, we will perform the same function again. But this time, we're going to pass in the left underscore child. And we'll use the same value. Cool. And then I can have the exact same logic for the right branch. But we have to change one thing, that being the side. So if the value is greater than node.value, then we're going to be checking the right branch. It is very tough to code on this laptop, by the way, because my computer is very old, so there are lines running up and down the screen, so I can't always tell if I'm spelling things correctly. But you should be good, hopefully. Cool. And then, so we have our condition set. If the value is not defined, we'll define it as being our new value. If the node is greater than the new value, then we'll check the left branch. If the node is less than the new value, we'll check the right branch. And it shouldn't be equal. And so do I need to add an else statement to check for anything else? Have I considered all the possible conditions? Does anybody have the answer in the comments? Let me check the comments. Okay, I'm not totally sure what you're asking, Moonstar, but there are tons of ways you can make a binary search tree. There's no like single way, so if you want to approach the problem different ways, that's totally cool too. Okay. I'm going to add one more else statement because potentially the value could be equal to the node value. That shouldn't happen because, as we talked about at the beginning, all the values in a binary search tree should be distinct. So I'll just like print out value already in tree. Exclamation mark. Awesome. Or I don't know, you can make like a try except statement or something else. Okay, let's try our function out. Is there anything else we need to do? Any ideas? Cool. Okay, so I'm going to make the first node. You can consider this being the root node. And I'll make it equal to an instance of the node class. And I don't have to pass in any value. It can be set initialized to none. And of course, how would I set the value? Using the set value function. So I can say root underscore node, and I can set the value being, let's say 8. Oh, sorry. So or I guess I could actually figure out this write, I can use the insert function instead, because we're using set value inside the class, sorry, inside the function to begin with. So I can say insert I can write root node, and my first value will be 8. And then I can print out what that value is just to make sure. So I'm going to write root underscore node. And how do I call the value property? With dot value. And then we can run that code. And then we do a quick double check. And I'll give you guys a chance to take a look at the code in case it's hard to copy. Cool. Okay, let's run the code. Cool. And as you can see, it printed out the first value of the node, which is node.value. And then we can add in another node. So I'd use the insert function once again. So I'm going to write insert. And once again, I'm going to pass in the root node, the top node, and the comparisons will go from the root node. And the next value we'll pass in, according to our test case, will be 3, I think. Yeah, 8, 3. But then let me just make sure by printing out the value of that node. So we'll print root underscore node dot left underscore child and then dot value. Cool. And then I'll add in the rest of the nodes. I think there's 6 in total. Okay, so we have 8, 3, 10, 1, 6. Oh, 5, my bad. Okay, so 8, 3, 10, 1, 6. Cool. Now I can run my module and create this binary tree, and I can call specific values of the tree. So we can quickly test our code. So if this is how our binary tree looks like, I can try to call specific values. So if I say print root underscore node dot, let's say if I'm going for the 6 node, so I can say print root underscore node dot left underscore child, and that'd be the 3, and then dot right underscore child and dot value. And what should the result be? 6, exactly. Awesome. Cool. So that is our first function that we had to implement. What is the next function we have to make? Well, we have to make a function. Let me maximize this. We have to make a function that will search for a value in the binary tree and return true if that value is in the tree and false if not. And this function will be called search. So I can make this function very easily. By the way, if we're looking for the proper or correct way to make the binary search tree data structure, generally these functions insert, search, depth, they would all be methods in a separate class called binary search tree. That's the more pretty way to do this. But in order to make that code, we would use some concepts that we don't totally understand yet. And I think it would just make the code a bit too confusing. So instead, we're just writing these as separate functions instead of methods in a class. This was actually a question on last year's midterm test, by the way. And once again, it's about marking by output. So as long as your output is correct, you'd get the full marks. Okay, so let's make the search function. So we're going to write def and then the function name, which is search. We can write find to just anything that denotes like looking for the object. All right, find, and we'll say node. We'll have two parameters: the root node that we're passing in and the value that we're looking for. Okay, so how would we go about finding a specific value in the binary search tree? What would that logic look like? Any ideas? Let me check the comments. So what type of computer logic should we use? I'll post the code in this description after, I guess. Yeah, that's a good idea. We totally can. Just here to save time, Moonstar, but you're totally welcome to make getter methods too. I made one setter method, so you can use the same logic to make your getter method. Yeah, conditional statements. That's perfect. Awesome. Okay, so our logic is going to be so I'll do it simply first, but there's a caveat you have to watch out for. I'll say if node.value, if that is equal to the value we're looking for, then we can just return true. Otherwise, we have to then look at half of the function. So I'll say if node.value, if that is greater than value, we're going to call this function again, but now we're just going to look at half of the tree. And so we'll say return find. Don't forget adding the return statement for a recursive function, by the way. Return find node dot left child. So now we're just looking at the left child, of course, because we're saying node dot value is greater than the value. Dot left underscore child and value. And else if node dot value is less than value, we will check the other half. Find and if neither of these conditions work out, if it doesn't meet either of these conditions, we would just return false. Cool. Okay, so is this code completed? Have I considered all of the caveats that I have to watch out for? Is there anything else I have to watch out for? Any ideas? Yeah, perfect. All right. Yeah, so we have to consider if it has no value. So we're going to wrap this all inside one big if statement. And we'll just say if node, if that's defined, then we'll bother checking to see if it has a value and or not. If it has a value equal to the one we're looking for. Otherwise, we'll just return false. Cool. Okay, so I'll give you guys a second to copy the code. I won't post the code in the chat just yet, but I will. I'll put it in the description after. And I'll also put in Nick's code too, or sorry, Mr. Moore's code too, because he did it a bit of a different way, but it's the same concept over again. And I figure the more ways you look at implementing a binary search tree, the better. Cool. Okay, and then we can test out our newly made function. So, for example, we can run some test cases. So we can say print find, and let's say we're looking at, of course, the root node, and we're trying to find a value 6. So what should this print out? Oh, that's not good. Print find root underscore node 6. Let me just check my code very quick. My apologies. Oh, my bad. Simple mistake. Sorry, I forgot to add the true. My apologies. I told you this screen, it's kind of wonky. Okay, let's run the code again. Perfect. Awesome. Okay, and for example, I run the same function, but this time I'm checking for 7. What should the output be? False. Perfect. Okay, let's make the last function that we'll be making together, and we'll talk about some additional tasks we can do. So the last function is the depth function. We have to make a function that finds the max depth of the tree. Okay, so take a minute and think about how we would accomplish this. There's a fairly simple way we can make the function. Any ideas? Okay, so we're going to write depth, and the function name will be depth. Yeah, so it's a simple idea. We're going to use recursion again and just increment by 1 each time. But yeah, good idea, Jeff, Neat, and Moonstar. Yeah, simple idea. You guys got this. You're experts. Okay, and we're going to pass in one parameter, that being the node, once again. And we'll say if node dot left underscore child. And how do we know if we reach the bottom of the tree, by the way? How do we know if our code is currently at the bottom of the tree? Any thoughts? What would I check for? What would left child be equal to? Or yeah, and a key thing is you have to recurse down both branches, as Moonstar said. Yeah, so you're checking for the none object. Yeah, none type. Cool, perfect. You guys got this. You guys don't need to watch the tutorial. It's so obvious for you guys. So node.left underscore child, and we'll say if that is equal to none, we'll set a variable called left underscore max equal to 0. As Moonstar said, we have to check both branches. Else, we'll set left underscore max equal to the value of the depth function, but now applied to that branch. So depth node dot left underscore child, and then +1. Perfect. And then we can apply the exact same code for the right side. So we'll say if node underscore right child is equal to none, then right underscore max is equal to 0. Then else, if it's not equal to none, we'll call the function again, but this time looking at just the right child. And don't forget to increment by 1 each time. Okay, and then we have these two variables that's finding the max in either side. And what should I return? Should I return both variables to get the depth? Yeah, so I can just return, and I can say max, and I'll just return the max from either side because the max depth should be the greatest yet. So return max, and I'll pass in both left underscore max and right underscore max. Cool. Yeah, Moonstar's got it, and Nishant and Japanese, you guys all got it. Awesome, great work, guys. Okay, now we can try to call our function and test it out. So what should the max depth of this binary tree be from the root node? Any idea what the max depth should be? Okay, let's run the code and we'll find out. Okay, 2, perfect, right? And that makes sense because if we look at our example, there are 2 layers to the binary tree. Awesome. Okay, so in terms of ways of improving the code, Moonstar already brought it up actually. So if we go back to our class, we have something called a setter function that sets a specific value. But we can also make a getter function that will return specific values like def get value, and that would return the value for a specific node. So that'd be a better way to get the value set for a node. And likewise, you can use the same concept for making left child and right child. So you guys can try to add those functions if you like. Yeah, and Moonstar, I think we talked about it before, but just like Moonstar said, great to bring it up again. So generally, these 3 functions would be in a separate class as methods inside a class called like binary search tree or something. And I'll actually post the code for how that would look like in the description. But one more thing I want you guys to think about, and this is your guys' individual challenge, and you'll have the rest of today to work on it if you like, is try to make a function that'll print out the contents of the tree correctly. So make a function that will properly print out the tree. To accomplish this, you have to use a concept called breadth first traversal. That's a hint. But given how quickly you guys got all the concepts we were talking about, as I can tell from the comments, I think it won't be too hard for you guys to make that print function. But if you can't get it, I'll post a video later on just to make sure we're all on the same page. And in addition to that, I'll post some helpful links in the description. Maybe not right now because I just have to attend to some things, but I'll post it as soon as I can. But in terms of improving the code, you can add the getter functions if you like. And what I think is the more challenging concept is you can make a function that prints out the contents of the tree correctly. Cool. Okay, so in terms of the midterm, it's online now. So I imagine you guys like that. I do, at least for my classes. And I'm sure you guys will all do well because the midterms I marked for midterm 2, they're pretty high. So I'm confident the mark should be high again. But just make sure you understand the concept of tree data structures. That's the main thing people usually mess up on. As I said, this was a question for last year's final exam, and the students didn't do too well. So I would make sure to go over the concept of trees. And fortunately, this is a live stream, so you can go through the code once again. And I'll post some more code after for other ways to implement the binary search tree. In fact, the way that Mr. Moore did it is a bit different. He still used one class, but he made that the binary search tree class. And that's a cool way to do it too. And I'll post the more common way using 2 classes, one called node and one called binary search tree, that you guys can go over on your own time. But again, keep in mind, as long as the code has the correct output, for a given input, you get the full marks. At least the way we mark it in this class. Okay, so yeah, stay in good health, guys. I hope you guys are all well, and that the quarantine isn't too bad, that you're not missing anything too important. And please make sure to stay in isolation while the recommendation is in effect. And I really hope you guys have a good summer, and best of luck with your upcoming midterms. All right, take care. I'll post in the description some more code you can look at, and I'll post another video on how to make the printout statement. But I want you guys to attempt that by yourself at first, and then we'll take a look at it together. And in terms of recommendation of a hint on how to do that, you need to use a concept called breadth first traversal. Once again, breadth first traversal. All right, take care. Best of luck. Bye. Okay, yeah, and like, share, subscribe too. Thanks, I appreciate that. I need all the subscribers I can get. I need the YouTube AdSense money. Okay, oh, the comments are here the whole time. That's useful to know. All right, take care, bye. Yes, thanks, Construction 3D, bye. And thank you, Panka and Japneet. Okay. All right, take care, bye, guys. Oh, that's very sweet. Thank you, Panka. All right, I'm going to say bye. See ya.